In the Arizona desert, about 130 kilometers north of the border with Mexico, there's a 3-acre oasis like no other on Earth. In many ways, it can be considered another tiny Earth with its own unique ecosystems, atmosphere, ecology, and chemical cycles. A parallel biosphere. The idea that became Biosphere 2 started with humanity's age-old dream to someday colonize other worlds. What would we need to survive on the Moon or Mars? If I want to sustain this fish, I could do one of two things. I could add oxygen and some food, or I could add a green plant, which through photosynthesis would do exactly the same thing. The green plant provides oxygen and nutrients for the fish, and the fish in return provides carbon dioxide and nutrients for the plant. In the same way, rather than technological life support, could a glass ark be built with water, air, soil, and plants, and sealed with a lid that would sustain human life indefinitely? There was only one way to find out. After billionaire Ed Bass agreed to fund the ambitious undertaking, and after years of design and planning, construction of Biosphere 2, with a modular space frame, 16,000 panes of glass, began in earnest in 1987. When sealed up, nothing, not air, soil, plant, or animal, was to exchange between Biosphere 2 and the outside world. It became the most tightly sealed greenhouse in the world. But a glass bubble in the desert has a special problem. It gets hot. During the day, the air trapped inside Biosphere 2 heats up and expands. Without a release valve for this pressure, the biosphere would pop. The solution was ingenious. Give it lungs. These take air expanding from the huge hot greenhouse during the day and release it back at night. But pressure is only part of the problem. The other is the tremendous heat. Maybe the biosphere wouldn't blow up, but without a huge cooling system, it would surely bake. The energy required is staggering. From a power station on site, large quantities of cold water are produced, pumped to Biosphere 2 through underground pipes and circulated in every part.
The energy I'm pumping into Biosphere 2 to keep it cool and keep it running is twice the energy Biosphere 2 receives on the outside, also on the outside of the glass.
In fact, everything we get for free on Earth costs energy and therefore dollars in Biosphere 2.
We're using mechanical means and pumping water to simulate cloud forming and humidity control. Rain we have to simulate by pumping water, running it through sprinkler heads.
Even the waves for the ocean are produced through machinery. The infrastructure for controlling and monitoring all systems within Biosphere 2 is huge and tucked away in a vast basement complex beneath biomes. Five wilderness biomes, rainforest, savanna, mangrove swamp, desert, and ocean, plus 2 human biomes, intensive agriculture, and a human living area, were each built to fulfill a function for the whole biosphere. So the tropical forest, with its rich vegetation, was to provide the bulk of the oxygen and remove the carbon dioxide, storing it as wood. The marsh and ocean would help remove excess salt and nutrients. The savanna and the desert would act as regulatory valves for the atmosphere. By providing rain, the biosphere managers could switch them from dormancy to productivity. When switched on, they would photosynthesize, removing carbon dioxide and releasing oxygen. So by turning the rain on and off, one could choreograph the composition of the air. Models had shown that intensive agriculture to feed people by cropping and composting rapidly was liable to produce huge oscillations in carbon dioxide levels. The idea was that by acting as sinks and reservoirs, the wilderness biomes would purify the water and stabilize the atmosphere.
Everybody loved it because then we'd learn twice as much and we'd have two things. The wilderness was to organize itself in hopes that the atmosphere would come out somewhere near the chemistry and stability of the planetary atmosphere, and then all they had to do about agriculture was worry about how to maximize their food production. But of course, some of the design choices to maximize production in the soil proved a fatal mistake almost.
So how do you build a biosphere? Of perhaps 30 million species within Biosphere 1's biota, only 3,800 were chosen to populate the biomes in Biosphere 2. Even so, this meant they would be a good test of ecological theory about what happens when species are packed together into a relatively small space. Theory says many of these species would go extinct, but those that remained would fulfill all the ecological roles and would reform into new communities. The system would self-organize. But no one had ever tested this theory before on such a large scale. Who would survive and who would go extinct? Some thought that all of the higher animals and plants would disappear and the system would collapse into a kind of a green slime. Bets were laid among ecologists as to how many species would survive. Some eminent ecologists guessed that more than 80% of the species would disappear. So, did the theory work?
Let me tell you about some of the changes, and then you can decide, maybe, for yourself. One thing that happened is in the savanna in the desert, we had several grasses that were planted there. And what occurred is that one specific type of grass became very predominant in both the savanna and the desert. That's not so surprising, but what's a little surprising is that it is a grass that has evolved in response to low CO2 concentrations, very high light, low moisture conditions, low nutrient conditions. So in Biosphere 2, that's reversed. So why did these plants do so well? I don't really know. Is that giving us a clue about something ecologically interesting? We're not sure. Now, what about the insects? The insects in Biosphere 2 were placed inside, just like the plants, in the beginning. A lot of the insects didn't make it. They went extinct. Humans were managing this place. Some of the insects may not have been able to obtain enough food. If you're a bumblebee, you want to have flowers and nectar. If you don't have enough of that, you're not going to make it. There were bumblebees in Biosphere 2 at one point. They didn't make it. What we do know right now is that the major insect populations that exist today inside are ants and roaches. And the ant apparently is a crazy ant, sort of a common greenhouse tramp species, which got imported into Biosphere 2 by accident. It's abundantly clear the ants are everywhere, all over this place. They're crawling all over me right now, and we have yet to understand what they're really doing inside. We've got to study this ant, and I'll tell you this is also very intriguing. The ants want to get outside because we see holes that the ants dig away in the caulking of the windows. We've seen ants go from the inside to the outside of Biosphere 2. So they're clawing their way out, and we're not really sure what they're doing out there or why they want to go back and forth. That's really interesting. In general, the biotic diversity in Biosphere 2 certainly has come way down from the original stocking of both plants and insects, and that, I understand, was the strategy employed by the designers. Fill it full of as much diversity in every way that you can, and you hope that at some point it will self-organize. And there'll be this mix of almost quasi-steady state plants, insects, and other biota that will sort of maintain vegetation and the biota at a given level.
So the biggest winners were ants, roaches, and weeds, like this climbing plant, Morning Glory. In fact, this was the exact prediction of the famous biologist Lynn Margulis, but most everyone else was caught by surprise. None of these winners was intentionally introduced. Still, around 70% of the original species survived, and none of the biomes collapsed. This was partly due to vigorous management by people. But in some ways, the theory was vindicated. Ecosystems did reorganize. Ecosystem functions previously performed by some species were taken over by others. In the ocean, the corals changed too, starting out like this, and now like this, supporting a vigorous growth of algae. The water pH was reduced due to high CO2. The new algal growth took over the function of photosynthesis and therefore carbon dioxide removal. Cockroaches, which had caused the extinction of many other insects, became pollinators in their place. The ecologists learned many lessons. Just how difficult it was to put together food webs where plants, insects, and other animals could coexist. But the biggest lesson was still to be learned. Would the system equilibrate to permit human occupancy and the perturbations that they would be causing with intensive agriculture? From 1991 to 1993, 4 men and 4 women were sealed up in Biosphere 2. Life inside Biosphere 2 quickly taught the biospherians not to take anything on Earth for granted. The most important of these is sunlight. Without sunlight, plants don't grow, the plants that provide food and oxygen. The special thick glass panes which could withstand the impact of a large hailstone had the unfortunate side effect of cutting out 50% of the light. So sunlight became the same as survival. By a cruel twist of fate, the weather outside made things even worse.
During the 2 years that I was inside of Biosphere 2, we had 2 very, very dark winters. By dark, I mean there are a lot of clouds, there are a lot of storms on the outside. Of course, we're tied to the light coming in through the glass for photosynthesis of the plants. Well, if it's a cloudy day, the plants aren't going to grow as quickly in general as if it's a sunny day. Of course, everybody would be crabby on cloudy days because that meant less food. So you're completely attached to the sun. You actually become a very sun-ruled community of people. We had a lot of sweet potatoes to eat, and we had a lot of bananas to eat, and a lot of beets. And those were, I think, our 3 big crops. We had sweet potatoes 3 times a day for our meals. Because there were cloudy winters, we had low production in our agriculture area, and we were hungry for a lot of the time when we were inside. And that made tempers a little bit difficult, because if you're hungry, you're not happy, generally not happy. We were healthy, but we were just hungry, so the sense of well-being wasn't what it would be for a well-fed person. So it was really a feeling of being a subsistence group of people in here, because we're very tied to the crops, to the sunlight, to the atmosphere.
Meanwhile, the atmosphere inside Biosphere 2 was showing some alarming trends. The wilderness wasn't really stabilizing things as it should. Slowly, but relentlessly, carbon dioxide was increasing. The biospherians began to monitor their air very carefully.
Outside, CO2 is maybe about 350, 355 parts per million right now, and presumably going up. On the inside, When we closed the door in 1991, I think we started about 400 parts per million. And during a certain time in the mission, it was several thousand parts per million, over 3,000 parts per million at one point, closer to 4,000 parts per million. Now that's an order of magnitude higher than what we have on the outside. It's very different. For every day of the 2 years that I lived inside of the biosphere, it was waking up at 6 in the morning or before and starting work. But the very first thing that we would all do was look at what the atmosphere was like. And we'd use our computers and find out how high the carbon dioxide was, what was the level of oxygen, was the nitrous oxide going up or not. Now imagine in your own world on planet Earth if you did that every morning, and if you had to make decisions for the day based on what your atmospheric composition was. Who would even think of it? Well, inside the biosphere we did that every day.
Dealing with the CO2 was to prove a major headache. At first, attempts were made to solve this problem naturally. The two safety valve biomes, savanna and desert, were put into maximum production. But there was a large price to pay.
Well, it looked like it was going to work fairly well for a while, but the carbon dioxide levels soared because the first winters were cloudier than expected, and of course there was more organic matter in the soil than was probably proper for such a closed system. And any effort to control carbon dioxide was made. The rainforest was already in full production. You couldn't do anything to that. The savanna was kept growing through the winter, and they were cutting grasses as fast as they could to stimulate regrowth. The only thing to do was double, triple the rainfall on the desert. Of course, you can't have a desert with triple the rainfall. John Allen called a meeting with me and said, you know, we've got this ongoing carbon dioxide problem, and we can no longer afford to have a desert. And this chilled me because I've been reading proposals lately that the world can no longer afford the luxury of unproductive deserts. Unproductivity is not inconsistent with a diverse, rich, fully functional community. But in this case, they couldn't afford it because they needed CO2 control. So John said we need to get 4 tons of wood a year harvested out of the desert. So I was to throw in as many quick-growing woody species into the desert as possible, and then keep the rainfall high and minimize summer drought so that we could try to get a very dense woodland that then could be cut every other year so that we could sequester as much of the carbon as wood as possible, so that we could stay materially closed but get the carbon out in the form of wood and dried biomass and store it in the basement where it was out of the system's circulation, somewhat analogous to the accumulation of coal beds on Earth. So as a result, the desert, receiving non-desert rainfall, transformed into a non-desert very quickly. In fact, astoundingly quickly. My estimate is I lost about 38% of my species, and about 20% more declined. Only about 8% of the total species really reproduced spectacularly well, and of the 5 greatest increasers, 4 of them were grasses. So the vegetation was telling me, you're not in a desert anymore, you're going to a savanna, which is, of course, exactly what you would expect.
But the attempt to decrease carbon dioxide by increasing plant productivity, even by sacrificing the desert, wasn't enough. The basic problem was there was too much soil and there wasn't enough air. Now, enough organic matter was put into the soils of Biosphere 2 to ensure its fertility for 100 years. This was the fatal mistake. For all of this organic matter was quite simply microbe paradise. Microbes in the soil decompose organic matter. In doing so, they release carbon dioxide, and they consume oxygen. Photosynthesis, which removes the carbon dioxide, simply could not keep pace. One of the beauties of science is that sometimes the most complicated processes can be expressed with the most simple equation. Take decomposition, also known as respiration. When bacteria and insects decompose organic matter, it can all be boiled down to CH2O, or organic matter, plus oxygen yields carbon dioxide plus water plus energy. If the carbon dioxide in Biosphere 2 goes up, the oxygen must go down. And in fact it did, month by alarming month. But then came the puzzle. To match 1-for-1 the oxygen that was disappearing, there should have been far more carbon dioxide in the atmosphere. There was only one conclusion. High as it was, the CO2 in Biosphere 2 wasn't nearly high enough. Something was removing and storing massive amounts of carbon dioxide.
Clearly, they put too much organic material in the soil so that the bacteria went, bananas and were eating up all this organic material and drawing down the oxygen. There's no doubt about that. The big problem, and the reason I got hooked on the place, was where did the CO2 go? And that was not a simple question. Jeff Severinghouse and I spent several months, and we went through all the possibilities. Could it be oxidizing sulfur in the soil? Well, sulfate being in the water, it wasn't there. Could have been making rust. That would have been 15 tons of rust. The place would have been just rust encrusted. And then Jeff's father said, well, why didn't you ever consider the concrete? Well, neither of us had ever realized that concrete starts out with a fair amount of calcium hydroxide, and then CO2 comes in, kicks out the water, and turns the calcium hydroxide into calcium carbonate. Jeff added up the area of concrete, and the whole basement is concrete, and the struts are concrete, so there's more area of concrete than there is of soil. And so it turned out that's where all the CO2 was, and actually it showed us how this place was self-controlling at the time.
In fact, this storage of carbon dioxide as calcium carbonate is exactly the same way that most of the atmospheric CO2 has been removed and stored on Earth. As one biospherian put it, rebuilding the White Cliffs of Dover. Furthermore, this completely unanticipated sink saved Biosphere 2, as it has saved Biosphere 1, from a very nasty situation.
So if they had built a biosphere without any concrete and put that much organic material in the soils, then they would have had a runaway greenhouse effect. CO2 would have gone up maybe during the winter months 400 to 500 parts per million a day. And if you do that for 90 days, you get up at 7% CO2. So that they would have had a huge CO2 problem.
Solving the CO2 problem was fascinating science, but it wouldn't help the biospherians. By late 1992, oxygen levels had sunk to 14.2%, and the people inside were experiencing effects similar to altitude sickness. Finally, the difficult decision was made. Biosphere 2 could no longer operate as a materially closed facility and continue to support humans. Starting on January 13, 1993, 475 days after sealing in the humans, some 14,000 kilos of liquid oxygen were injected into the lungs over a 19-day period.
Now, when that happened, all of us on the inside thought, this is so exciting. We're finally going to have enough oxygen. We all raced down to the lung, got into the lung while oxygen was being put in. And I could tell immediately, the difference between this low oxygen level, which would be similar to about 14,000 feet on a mountain, versus what it was like to having 26% oxygen. It was wonderful. I spontaneously started running, and I hate to run. I never run, but I just had so much energy. It was like a dark cloud lifted from my whole being. I felt much better. So it was a relief to see that that's why there were a lot of negative feelings on the inside. At least to some extent, that was a cause.
The biospherians then completed their 2-year mission and came out into Biosphere 1 in autumn 1993. In one sense, a victory. In another, a defeat, because by pumping in oxygen, humans effectively were added to the list of species that didn't make it inside Biosphere 2. The only way they survived was with outside aid. There are no plans to seal humans in Biosphere 2 in the foreseeable future. Since January 1996, when the Lamont Doherty Earth Observatory of Columbia University took over, Biosphere 2's scientific programs have been overhauled.
Professor Brocker, can you tell me something about what makes Biosphere 2 unique for, say, ecological or biogeochemical research?
Well, first of all, it costs $150 million. That automatically makes it unique. But, you know, the Earth is going to have higher CO2 content, and whether it's going to make it warmer or not, we don't really know. But we do know that higher CO2 will change the way plants operate and allow us perhaps to grow more food with less water. It'll change the competition among plants. So the fact that we can control the atmosphere in here, keep the CO2 content where we want, those are things that together nobody else can do. I don't think the combination of large plants and closed system, you know, where you can budget carbon and water exists anywhere else.
These unique advantages of Biosphere 2 will be put to use in a research program operating within strict scientific guidelines. The response of both individual plants and the entire system to changes in greenhouse gases will be studied in the wilderness biomes savanna, desert, swamp, and rainforest. The agricultural area will be subdivided into 3 parts to understand the greenhouse effect in finer detail.
We're going to operate it probably at 3 different CO2 contents, or another option at 2 different CO2 contents, and then at the high CO2 ambient temperature and 3 or 4 degrees warmer. So one of those bays then would simulate a world where the CO2 went way up, which is going to happen, but there was no particular warming, and the other one would be a world where the CO2 went up and there was warming.
With any luck, Biosphere 2 will fulfill its mission of becoming a world-class center for study of Earth system processes. The self-contained space colony, the utopian Eden, failed expectations. But by shedding light on how ecological communities work and how chemical cycles function on this Earth, Biosphere 2 has already been a success. The many surprises have spawned dozens of new research projects. Finally, Biosphere 2 has pointedly reminded us that big as it seems, our Earth is still just a closed bubble too, one in which soils, vegetation, atmosphere, and humans profoundly affect each other.
I always think back to the lessons I learned here and to the finite boundary that I can feel, that I can't feel outside, but it's still a finite boundary even though we can't touch the glass.